Okay, so I'm going to go through about half of your review questions. I'm not going to go in order, but I'm also not going to write down the number that I'm doing. So you're just going to have to listen to this video, not just skip to the end of each problem and hopefully copy it down in the right place like I know a lot of you have been trying to get away with doing. So we're going to start out with number 2. An object is located blank centimeters to the left of a convex lens that has a focal length of blank centimeters. State where the image is formed, or state where the image formed is located, and name 2 properties of the image. Alright, so let's first just work out, let's identify it's located blank centimeters to the left of a convex lens. So with all of these problems, it's a very good idea to draw a picture. So let's do that first. Let's say here's our convex lens. Our object is located some distance from the center of it. So from here to here, we have a given distance. We know this as our object distance, or O. Let's say that O in this case is, let's go with 8 centimeters. Okay, and then our focal length is, let's go with 2 centimeters. So normally, you don't have to draw any pictures, but it might be a good idea to learn how to do it. So let's say this is 4, this would be 2, so this is our focal length right here if it was on that side, and this is the focal length here if it's on this side. So the focal point is 2 centimeters away from that length. It could be this side or this side. It really all depends on where this object is located. We'll talk about that more later and a lot tomorrow. But for right now, I just want you to know that if the object's distance is greater from the lens than the focal length, then the focal point is going to be on this side. That's just the point where if any light ray was passing parallel to this line right here, it would be passing through the focal point after it went through the lens. So we have an object that's here. Let's put it right there. And then this is our focal point, either on this side or this side, which is 2 centimeters away from the center of the lens. Okay, so the formula that we're going to use for these, it's called the thin lens equation, is that the inverse of the focal length is going to be a summation of the inverses of the object's distance and the image distance. So jumping back to the problem, we want to know where the image is formed, and we want to name 2 properties. So first things first, little algebraic review. We're looking for this I right here. So let's subtract by 1 over O on each side. We did this a lot on Friday. Well, I did it for you once on Friday, but I'll do it for you once today again. 1 over the image distance is equal to 1 minus the focal length minus 1 over the object distance. Okay, so we want to get I alone right now, and it's going to be a lot easier if we combine these 2 fractions. So what we're going to do is multiply this fraction over here by O over O. That way they can have a common denominator of O times F. Multiply this fraction over here by F over F, which is really just 1. Anything divided by itself is 1. If you multiply anything by 1, you just get the same exact fraction, so you haven't changed it. So algebraically, 1 over the inverse of the image distance is going to be equal to O times 1 is O. minus 1 times f is f divided by O times f. So now that we have a common denominator, we can change this into one fraction. Okay, so one final step to solve for the image distance. We're going to invert this fraction. You could go through the long process of cross multiplication, but just take my word for it. If you take a fraction to the -1th power, you just replace the numerator and denominator with each other. So you get the image distance is equal to the product of the object's length from the center of the lens divided by the difference between the object's length and the focal length. Okay, so now we're ready to plug these numbers in. I chose 8 centimeters for my object length, and the focal length I chose +2 centimeters. So let me finish writing this out and then talk for a second about how the focal length being positive really says something about where the image is at. So whenever your focal length is positive, I should maybe write this down here. If f is greater than 0, not the object distance, 0 numerically, then the image is on the opposite side oops. Now this is key here, lens. If we were talking about mirrors, this would be, opposite would be replaced with same. So whenever your focal length is positive, what that means is that the image is formed on the other side of the lens of the object. So when I say opposite side, I mean opposite of the actual object. So that's how you know that this is going to be a positive number right here. If the focal length is positive, then your image should be positive. And so that brings us to our next little statement we want to make, but let's finish this. 8 times 2, that's 16 square centimeters. 8 divided by 2, that's 6 centimeters. So 16 divided by 6, let's see here. Oh, that's 16 divided by 6 is 2 points repeating 6. So my image distance is 2 point repeating 6 centimeters. Okay, that right there is 2 points. Now, another thing that you need to know, if your eye, your image distance, is greater than 0, meaning it's a positive number, then the image that's created by this lens, and in this case it's the mirror too, the image will be inverted, meaning upside down, and real, meaning the light rays actually do come together. So this is where it's very hard for me to do a good job drawing a picture illustrating it, but you know, if you had a light ray that was coming, that was parallel to this, it's called the principal axis, you don't need to worry about that though. It's gonna come through here at this focal point. If you have a light ray that it goes through the focal point on this end right here, when it hits the lens, it's going to end up on the other side coming out straight. And if you have a light ray that goes right through the center of the lens, meaning it doesn't hit it at an angle, it actually hits it at an right along with the normal line, then it's going to pass straight through without bending at all. And your image is going to be formed right here, upside down. So it's really hard for me to draw it on this. Hopefully some of those pictures in that packet you got on Friday help explain it. But so this is a real image because the light rays come together, and it's inverted because it's upside down. Think of its orientation. Before, the top of it was facing towards the top of the screen up here. Now the top of the image is facing towards the bottom screen down here. So the full answer for this, 2-point repeating 6 centimeters, and the image is inverted and real. That right there is worth 4 points. You get a point here, that's kind of a gimme. This whole thing, all you're dealing with is distances, so pretty much every single answer should have centimeters unless I used a different distance unit, and I did on some of them. So 2-point repeating 6 centimeters, and the image is inverted and real. How do you know that? Because the value we calculated for I is positive. And it's usually going to be, they're not usually, always going to be the case if the focal length is greater than 0. And another thing that I should put, if O, and this is not 0, this is this O, if the object is further away from the lens than the focal length, and this is true for mirrors, true, then the image will be inverted and real. Now this is actually not true for concave lenses or convex mirrors. So over here we should probably put convex lenses. And it's also true for concave mirrors. So there's all sorts of little tricks that you could use to help you realize if it's going to be inverted and real. The main one that I think would be the best use for you is comparing I to 0, and you're going to have to make this calculation first. However, sometimes you're going to have to assign the focal length as being positive or negative depending on the situation that you're being given. So this is the easiest one to remember, but it might not be the best one for you depending on the problem. Okay, so let's move on to the next problem. Hopefully the other ones will go a little bit faster than that. All right, so we're going to move on to number 3. An object is blank centimeters to the right of a convex mirror, and an upright virtual image is formed, blank centimeters to the mirror's left. State the focal point's position using its distance and direction. So you need to state where the focal point is, and we need to state how far away it is. So I guess where is how far away, but how far away it is, or where it's at relative to the object, which side I mean. So again, let's start out with a picture. We have a convex mirror. So up top here, let's draw a mirror that is convex, meaning it's bubbling out, just like the last problem. I'm not going to draw a double because it doesn't really matter. It's not going through. It's only one side that needs to bubble out in order for this to make sense. Okay, and let's see. I know that my image is formed on the opposite side of the mirror. So the object is to the right of it, and the image is formed to the left of it. So let's state this object's distance. Let's go ahead and give it a distance of 12. So we're saying this object is 12 centimeters away from this mirror. Whoops. So here's where this object is at, 12 centimeters on this side of the mirror. And we're going to say that its focal length, or no, I'm sorry, its image, where it appears to be, is, let's say 4 centimeters. So we're going to say this object is 4 centimeters. So it should be about 1/3 of this. It's probably pretty good. Okay. So what we want to know here is the focal point's position. So where do the light rays appear to converge from? So that's the thing here, is this is an upright virtual image is formed. Now if you're told that a virtual image is formed, that right there tells you that I is negative. So we need to jump back here and change this. I is 4 centimeters, but it's 4 centimeters in the negative direction. Now you should note, last time we were dealing with lenses, and when it was on the opposite side, it was positive. This time when you're dealing with mirrors, if I is on the opposite side, it's negative. So maybe we should write down a quick little sentence here. When the image is virtual and upright or erect, I is going to be less than 0. Okay, now this is true for all lenses, all mirrors, doesn't matter what type. This is a true statement all the time. So some of these problems are difficult because you have to assign a negative number. I didn't just give it to you. I want you to understand this connection here. So this is something that you're going to need to know when you walk in on Wednesday or Thursday to take the quiz. Now, we're dealing with the same equation as last time. The focal length, which is what we're solving for, is going to be equal to 1 divided by the object distance plus the image distance. So we need to do some manipulation here. Now I want to solve for f, but first let's change this into one fraction. We're going to multiply by I over I, which is really just 1. Multiply by O over here, which is 1. This way we'll have a common denominator of I times O. That gives us the inverse of the focal length is equal to I times 1 is I, plus 1 times O is O, divided by I times O. Alright, we're almost done. We just got to invert our fractions here by taking them to the -1th power. And you find that the focal length is going to be equal to I times O divided by I plus O. So we're ready to plug our numbers in. I is -4 centimeters. We know that it's a negative number, not because it was given to us in the problem, but because we were told we have a virtual upright image. The object's distance is 12 centimeters. And the summation, so -4 centimeters plus 12 centimeters. Okay, so this is -48 centimeters squared divided by -4 plus 12 is 8 centimeters. Okay, so -48 divided by 8, and then our centimeter squared cancels out with our centimeter, and our focal length is going to be equal to -6 centimeters. Whoops. What's going on here? Sorry about that. Okay, so what does that say about our picture up here? Because we do have to say something else. So what that means is out here, this is where our image is formed. So what that means, if our object is over here, In this one, there's no way I'm going to be able to draw and make it look good. If the light was coming straight and bounces off the mirror or reflects, it would appear as if it emerged from this point. Let's see, if I had one coming straight on towards it, it would bounce back. Going away from it, it would appear as if it was emerged from this point. And then let's see, -6 over here, so 6 over here. So if light came through halfway here, if it bounced, it would bounce in the negative direction. Or wait, bounce like this, and it would appear as if it was coming from this point. Or no, I'm sorry, that's wrong. But anyways, what you need to know for these ones, this light ray didn't do the trick for me. Let me get rid of that last one. This one would, it would have to be headed towards the focal length and then bounce off, and then look like it was coming from this point. So this one's really hard to draw. But anyways, what I'm saying is the image back here gets formed. They should all be looking like they're emerging from this point, so obviously I didn't do a good job drawing this picture. Hopefully you get what I'm saying. But anyways, this focal length is negative because it is on the opposite side of the object, but that's because we're working with mirrors. So it's virtual and upright, but the other part that the problem is asking you, or what it's asking you for, is not just the distance, but also its direction. So if my object is located on the left side, then my focal length, or my focal point, is -6 centimeters to the right of the mirror. So these pictures up here that I'm attempting to draw, I'm not really doing a good job. You can see a good picture in that packet that I gave you that does some justice to what should be shown here. The main thing that you need to be able to do is take note, it's a virtual upright, that means I need to set I to negative. You're going to get a negative focal length then, meaning that the image is formed on the opposite side of the mirror, and that's how all convex mirrors work. Maybe we should write that down. All convex mirrors. And I should write, and concave lenses form virtual images. And those virtual images are always upright as well. So, convex mirror and a concave lens, they always form images where it appears as if the light is coming from a specific point. Okay, so moving on. Let's see. I'm gonna skip down to number 6. So an object is located blank centimeters to the left of a concave lens with a focal length of negative blank centimeters. So this time I am giving you a negative number. On your test, I don't think I did. You might just have to assign it. So it's to the left of a concave lens. It's got a focal length of negative blank centimeters. You need to state where the image is formed, or where the formed image is located, and name the two properties of the image. So this is just like the second one that we did, number 2. Okay, so let's get our picture going. Blank centimeters to the left of a concave lens. Let's go with, well, first let's draw our picture. concave lens bends inward. We just wrote a statement about concave lenses on the last slide. They always form a specific type of image. Hopefully you know what I'm talking about. Get our principal axis, or the line that goes straight through. Let's put this out there. Let's say our object distance is, I don't know, let's say 6 centimeters here. And we'll give it a negative focal length, which means for a lens, the focal length is on the same side as the object. We'll say that that focal length is, so let's say this is O, and this focal length we'll say is negative, let's see, this is, I don't know, let's say -2. Okay, so looks like we're missing the eye. That's probably what we need to find. Where the image is located and 2 properties of it. Alright, so we want to find out what eye is. I already did this a bunch of times, and we already spent 25 minutes on 2 problems. So let's speed things up here. I equals O times F divided by O minus F. You could try to memorize this problem if you want, if you're not trying to do all that algebra, but you're likely to make mistakes. So I think it's better that you just learn how to do the algebra. So we have our O here of 6 centimeters. Our I is negative. Concave lenses always form virtual upright images. So I kind of gave you the answer, or at least half of the answer. Now here's where you have to be tricky, or have to be careful. It can be tricky. You're subtracting a number that's negative. So here's where I usually change my parentheses into brackets on the outside, and so I can use parentheses on the inside. Alright, 6 times -2, that gives us -12 centimeters squared. And now we have 6 minus -2, which is the same as saying 6 plus 2. 6 plus 2 is 8 centimeters. Let's see, 8 goes into 12 one time, but it's -12, so that's -1 point. There's 4 left over. 4 divided by 8 is 5. Our square centimeters cancels out with these centimeters, so we got -1.5 centimeters. So where's our image going to be formed? Looks like it's going to be formed 3/4 of the way to this focal point, so right about here. So I'm not going to do a terrible job at trying to show you the light rays emerging from this point, but you know, if I come over here and just show you how light passes through a concave lens, it always bends outwards. So it kind of makes sense that the only possible image that could be formed is one that is virtual and upright, meaning the light rays are never going to come together out here because they're only being bent outwards from each other. So the only type of image that could be formed is virtual, and the same goes for a convex mirror. Any light rays that bounce off of this are going to be bending away from each other. So the only type of lens, or the only type of image that could be formed is a virtual one. So hopefully this helps you make sense of that statement that I made on the last slide about how concave lenses always form virtual images as well as convex mirrors. So this -1.5, this is only 2 out of 3 of the points. The other one is you need to say in which direction. Well, if our object is on the left and we have a negative focal length, when you're talking about lenses, that means it's on the same side, whereas if you were talking about mirrors, it would be on the opposite side. So -1.5 centimeters to the left of the concave lens, which is the same exact side as the object. Let me double check that and make sure. to the left of the lens. Okay, so we're going to take a break from lenses. We're going to try, let's do number 8 now. An observer's height is blank centimeters, and a telescope makes it appear to be blank meters away from an observer. When, that's kind of worded weirdly, sorry about that. It should say makes him or her, or it is fine, I guess. Makes them appear to be blank meters away from an observer, when it is actually blank meters away from them. So, what we have here is an object's distance, an image distance, and I guess a magnification factor, which isn't really that hard to understand. Let's move on to a new layer here. So how much something's been magnified is really just the quotient of the image, how far away it appears to be, as well as the object's distance. And there's a negative sign out front here. And that negative sign just has to do with whether or not that image is real and inverted or virtual and upright. If it's virtual and upright, that makes this negative, which cancels out that negative. So this means our magnification factor will be positive when the image is virtual and upright. And if this is positive, then this is going to be negative, then this whole fraction is negative, meaning our magnification factor is going to be a negative number. It doesn't really matter. It gives you a little insight about the image that's being formed, but most of the time when you're magnifying something, you are forming a real image. So this negative sign kind of doesn't really need to be there in my opinion, but that's just me. So jumping back to the problem. So the telescope makes it appear to be blank meters away from an observer when it's actually blank meters away from them. So the appearance is the image, and where it's actually at is the object's distance. So let's just choose any two numbers here. Let's say that the image looks as if it is, I don't know, let's say 15 meters away. So it makes it appear to be 15 meters away, but it's actually, let's say, 5 meters away. So what's the magnification factor? Well, that means -3 times. So you might be thinking, hold on, things that are further away look smaller, so how come this magnification factor is larger? It doesn't have to do with this negative sign, it just has to do with, if you think about something that is further away but looks the same size, must mean that it's bigger, because if you got closer to it, it would look a lot larger. So if something makes something look further away, but it keeps its size, that means it would actually increase in its size. Like if its vertical distance vertical height remain the same, but it appears to be further away from you, then it actually would look a lot larger. It's kind of hard to understand just listening to me talk about it, but I guess you're gonna have to take my word for it or think about it like a, I don't know, like a building. Okay, anyways, moving on. So we're not really done with this one. We just found the magnification factor, but we said, okay, the object's, the question's kind of worded a little weirdly, so hopefully this review will help you out with it. An object's height is blank centimeters, and a telescope makes it look to be this far away when it's actually this far away. So the object's height, that's how big something is. So let's just say this object has a height of, I don't know, let's just say 4 centimeters. So how large does it actually look to the observer? Well, you just have to multiply the magnification factor by the height of the object. There's not really any formula for this, you just have to think about it. If it's actually 4 centimeters tall and something magnifies it to be 3 times, Well, what's 4 times 3? It's going to appear to be 12 centimeters tall. So there's no formula to memorize. You're going to be given this. You just have to read the question, figure out what is the image distance, what is the object's distance, what is the magnification factor, and then multiply that by the actual distance or by the actual size of the object to see what it appears to be, how it looks to the observer looking through the microscope. Okay, so the next one, only about 1/4 of you are going to have to worry about the first part, but I want to make sure all of you are ready for it just in case. A beam of light reflects off of an object located blank meters away from an observer. Oh, looks like there is an error on your review. So when you get your review, don't worry about that P. It's not supposed to be there. It's supposed to just be 180. The 0 key is right next to the P key, so I accidentally typed that one too many times. Okay, so how far away is this object? The observer goes from the air into the lens of their glasses and slows down to 180,000 kilometers per second. Since the index of refraction for air is 1, what distance does the image seem to be for the observer? So there's a couple things we have to do here. First, we have to figure out the index of refraction for their glasses, and then use a formula that was shown to you on Friday. So let's get a new layer going here. So a couple of formulas we need to use. You need to use the formula for the index of refraction. This was introduced to you on Fridays due now. It's the quotient of the speed of light and the speed through which light travels in the medium. That's how you find the index of refraction for the medium. And the other formula is to find out an image distance when you have an object's distance and you know the two indices of refraction. So we're looking for this, we're given this, and we also need to just choose any random value for that. So let's just say that O is equal to, I don't know, let's say 10, was it meters or centimeters? 10 meters. And we know that the velocity that the light is traveling when it goes into their glasses is going to be, or is 180,000 kilometers per second. So that is our V. 180,000 kilometers per second. Alright, so first we need to find the index of refraction for their glasses. So you will also be given this. The speed of light is 300,000 kilometers per second approximately. So the index of refraction for their glasses is going to be the quotient of 300,000 kilometers per second divided by 180,000 kilometers per second. So we'll pretend like, light in air pretty much travels the speed. It goes a little bit slower than that, but it's so close to it, they just say that the index of refraction for air is 1, which means anything, this would be 1 right here, or 300,000 to make the whole thing 1. But when it goes through a medium that's much thicker than air, like glass or water, it slows down pretty significantly, and that's why it bends or refracts. So if I divide these two numbers, what I end up with is 1 point repeating 6. It just comes out to like 30 divided by 18, which reduces to, let's see, I don't need to do it, 5/3 or something. Anyways, you get 1 point repeating 6. And notice that our units all cancel out, so the index of refraction is a unitless number. But now you need to ask yourself, is this N1 or N2? Is this the second or the first medium that the light's traveling through? So It reflects off an object located blank meters away. We said that's 10. And then it goes from the air into the lens of their glasses. So from the air into the lens. What that means is that the lens, which is the substance that this light is traveling the speed through, is the second one. So this is N2 right here. And N1, the index of refraction for air, is just 1 because we say light travels pretty much this speed in air. Alright, so that's it. We have everything. We want to find our image distance. We know that our object is 10 meters away from the lens. Or you want to think about this as like a person's wearing glasses. Some of these problems, it might be a good idea to try and picture what's going on here. There's an object. Light strikes the object. It's traveling through the air, and then it goes into their lens. What we're talking about is how far away does this image appear to be? We know that it's actually 10 meters, but for this person wearing the glasses, how far does it appear to be, given that these glasses refract the light, slow it down by this much? So we have everything we need. We just need to plug it into this equation. I just wanted you to know what we're actually solving for, what this object look, or where it looks like it's at for the observer. Alright, so the object's distance is 10 meters. N2, this is the lens. Remember, this is the second medium that it's traveling through. 1 point repeating 6 divided by 1. That's the index of refraction for air. Alright, so 10 times 1.6, about 16.6 meters away. So this object looks further than it actually is to the observer. So those glasses are, I guess, making things look further away. I don't know what that means about if they're nearsighted or farsighted or what. Okay, we are more than halfway done. Let's see, how much time have we been spending here? I might not, yeah, it's been 42 minutes, so try to finish this up in the next 8 to 10 or 8 to 15. Let's jump back into some more thin lens problems. Those are the ones that will be difficult. That'll be the difference between a and a B, B and a C, or possibly pass and fail. Okay, new layer here. The next one I'm going to do is number 10. An object is blank centimeters to the right of a convex lens and forms an upright virtual image blank centimeters to the right of the lens. So you're told something right there about the value of I, which will be given to you on the test if you get this version. But we're going to have to assign a number because it's virtual and upright. So let's draw our picture. We need to impose some, we need to make sure that our object is closer to the lens than our focal length. Oh, we're solving for focal length. So I guess it doesn't really matter that much. Alright, so we have a convex lens. Let me make sure that's what we're working with here. Yeah, convex lens. Alright, so we have an object close to a convex lens. Let's say that it's 4 centimeters away. So this distance right here is 4 centimeters. And it forms a virtual upright image blank centimeters to the right of the lens. Alright, so this you're not going to have to worry about this because it's going to be given to you, but if it's forming a virtual image, what that means is that this object must be closer to the lens than the focal length. So this image is going to be negative because it's virtual and upright. So let's say that this image distance right here, this whole thing right here, is going to be 6 centimeters. But since it's virtual and upright, we are going to need to assign that a negative 6 centimeters. So that's going to be the tricky thing for a lot of you, or those of you that are going to be close to solving these, is that if you are dealing with virtual upright images, you need to assign the values of your image to be negative numbers. Alright, so we're looking for the focal length. It should be obvious that this focal length is going to be a negative number. It's going to appear as if these light rays are emerging from a point back here if the image or the object is right here. So let me just like shade this in. This is our object right here. Okay, so we're looking for the focal length. I've already done the algebra for you on this one. You can refer back to that slide. The focal length is going to be the product of the image distance, the object distance, divided by the summation of the image distance and the object distance. So my image distance is negative 6 because it's virtual and upright. My object distance is 4 centimeters. So negative 6 centimeters plus 4 centimeters. Alright, so negative 6 times 4, negative 24 square centimeters. Negative 6 plus 4, negative 2 centimeters. Negative 24 divided by negative 2 is positive 12. Square centimeters cancels out with these centimeters, and you get 12 centimeters. Now, it might seem as if this focal length should be back here, but the focal length doesn't change just because the object is closer to the lens than the focal length. Like that, if this is 4 right here, then we got to go 1, let's see, 2, 3. So our focal length is all the way back here. But that would be the negative focal length. That would be for a concave lens. The focal length for, they call them positive lenses in your books, but for a convex lens is always on the opposite side of the lens. So even though the image is formed behind it, like this object looks like it's coming from back here because of the way that the light rays bend. They're going to appear as if they're coming from back here. Well, I don't want to try to draw this all over again. But our focal length is a positive number, which means it's 12 centimeters to the, if our object's to the left, to the right of the lens. So I guess there's a couple of rules that we should write down real quick. For convex lenses and concave mirrors, always have positive focal lengths. And that's even if they're forming virtual upright images. Like this is forming a virtual upright image, but that doesn't mean that the focal length isn't on this side. So if this, if I have a line right here traveling straight parallel to the principal axis, it will bend and pass through the focal length accordingly. It'll just appear as if it came from back here, because if I follow this line back right here, it would appear as if it was coming from right here. So For these ones, for both convex lenses and concave mirrors, if the object's distance is less than the focal length, like look at this, 4 centimeters is less than 12 centimeters, then a virtual upright image is formed. So this is true only for these two things right here. For convex mirrors and concave lenses, they're always virtual upright. So this is the one scenario for these two where that's what you're going to get. Okay, moving along. Now we're going to jump to number 14. Getting close to the end here. A real inverted image is created blank centimeters to the left of a convex lens. Wait, I want to do 13 actually. No, I don't. I want to do 14. But, and you know what, in the interest of time, I think I'm just going to I'm going to skip 13, I'm going to do 14 and then call it a day. So I'm not doing all of the half of your homework for you like I normally try to. But I want to make sure that you can see all of these in class today and not try to skip out on one. So an object is located blank centimeters to the left of a concave mirror that has a focal length of blank centimeters. So it's located blank centimeters to the left of a concave mirror with a focal length of blank centimeters. So let's draw this picture. So I have a concave mirror. I have an object to the left of it. Let's say that this object's distance is 3 centimeters. And let's say that the focal length is 6 centimeters. So what that means is a ray that was traveling parallel to this principal axis is going to reflect and pass through this point 6 centimeters away. Okay, that's what the focal length means. Alright, so we want to find the image distance, but we also want to know two properties of that image. So where it's at and name two properties. Okay, so the image distance we already know. Product of the object's distance times the focal length multiplied by or divided by the object's distance divided by the focal length, or subtracted by. Alright, so we have 3 centimeters times 6 centimeters subtract or divided by the difference between 3 centimeters and 6 centimeters. Okay, so what do we get up here? 18 centimeters squared, not cubed, divided by -3 centimeters. So our image distance is going to be equal to -6 centimeters. So what does that mean? Does that mean it's here? Now, since the object is closer to the mirror than the focal length, my image distance is going to be out here on the other side. So since O is less than F and I is less than 0, the image is, and you should all know by now, virtual and upright. Okay, so I think that covers it. I mean, I didn't do number 13. Number 13 is pretty easy. in comparison to the rest of them. I'm sorry, number 14. That was number 15 that I just did. But number 14, the only thing is you're going to have to assign that negative number, and we already covered that. So hopefully that gets you ready for the rest of this assignment and your quiz. We got it done in 55 minutes, which hopefully is enough time.